Yes, I will be here. I definitely want to. Definitely, yes, I want to talk to you too. Awesome. You guys hear me okay?
Yeah.
Yes.
Yeah.
Perfect. Thank you. Thank you. Awesome. Yeah, quiz is getting ready to start, so I'm going to just make an announcement as soon as it goes live here. Okay, guys, quiz is live. So go ahead and hop on in the next 2 minutes, and you'll have 6 minutes once you hop on.
Professor,
Go ahead.
for the second question, it's kind of blurry. So is it
Is that the one with the thermometer on it?
yeah.
Yeah, just do your best to read to the nearest degree. I think the answer will pop out and be obvious to you.
Once we're done, does it give us a score once the time?
Yeah, I think it actually does
Yeah.
that for you. It should give you the feedback once you're completely done.
Okay.
And it may actually happen after the quiz closes out. Okay, looks like we're finally closed out. What I can do is take a quick look at it just to see how folks did in general. So you have the 100-gram sample. Looks like on that one, about 43% of the folks got that right. That's good. Second one, the gold medal density one, looks like about 52% of the folks who took the quiz got that one right. And the temperature one, looks like 70% got that one right. Okay, so not too bad, guys, for your first time out. All right, I'm going to pop out of Chem 101 here for a little bit, and I'm going to pop back over to the notes. And what we're going to do is sort of finish up with conversion factors and dimensional analysis here. So this is, again, a skill that we're going to be using pretty much throughout the semester. So we want to make sure we've got this down pat. All right, so one other kind of conversion factor that we occasionally have to work with, I won't even say occasionally, we do it often, is to focus on concentration. Okay, so when we talk about concentration, what we're dealing with here, guys, is resolution of a mixture. Okay, so we're talking about, for example, a liquid solution, but this doesn't necessarily have to be the case. Okay, so if I were to resolve a mixture and look at the different parts of it, okay, you're going to have the solute, which is the part that gets dissolved. So for example, if I'm making a solution of, say, salt in water, the salt is the solute because it gets dissolved up in the water. Okay, and I could talk about the grams of solute that I put in the solution. Now also you have the solvent. So in this case, that would be the water, right? Because that's the part that's doing the dissolving. I could also take the mass of the water involved in the solution. Now, as it turns out, if I want the total mass of the solution, masses of solute and solvent add together, okay? So ultimately what I could do is I could add these together and I could get the total mass of the solution. And that would be in grams as well. All right. Now, as it turns out, sometimes we'll deal with volumes. It turns out volumes don't add, but masses always do add if we're talking about solutions or mixtures like this. Now, if I want to express a concentration of, say, solute in solution, one way I can do that is by way of something called a percent by mass. Okay, a percent mass. Now, what this is just going to be the ratio of the mass, and we'll just say grams of the solute, which is what gets dissolved, divided by the total grams of solution. So that's grams of total solution. And then if I want to turn that mass ratio into a percent, obviously I have to multiply it by 100%. Okay, so that's a way of stating a concentration or a composition of our solution from a quantitative perspective. So I could use a percent mass, for example, as a means of moving between, let's say, a solution and a solute in a problem. Okay, so it gives me a relationship between those two things. All right, also, just let me think of it another way. If I had a situation where I had a mass ratio of, let's say, 10 grams of salt per 100 grams of solution, okay, that would be the same thing as saying I've got a 0.1% by mass, okay? So I could express this also as a mass ratio if I want to, and we'll use that as a conversion factor as well. All right, so let's take a look at an example that uses this. So this is one that I actually kind of do in my daily life. I don't know if you guys have ever enjoyed or tried kombucha, but it's a fermented tea beverage. Anybody tried it? Anybody make it? Some of you guys actually make it, I'll bet.
I've made
Anybody
it.
know? Yeah, so you've made it. Okay, good. So it's something you can brew at home if you want, and there are a lot of brewers that actually produce it and sell it at farmers markets and in co-ops and things like that. So actually, one of my students and I are starting a company to analyze kombucha. So we help kombucha manufacturers and brewers, for example, do quality control or quality assurance, and also help them, for example, develop food labels for their product. So one thing that often has to be done if you're developing a food label for kombucha is you have to determine the sugar content. And this is a big deal. For example, if somebody who's drinking it happens to be diabetic or something like that, they want to know how much sugar is in the kombucha in a given serving of the kombucha, and that has to show up on the food label. So this is something we do all the time. Okay, so this is a real world, and this is actually based on pretty much real data that my student and I get. So it says here a sample of kombucha has a sugar concentration of 3.5% by mass, and that's a measurement we can make independently of the kombucha. And the kombucha itself has a density of 1.0231 grams per milliliter of it. We want to calculate for a food label, for example, the grams of sugar in an 8 fluid ounce serving, which is sort of a standard serving size of the beverage. And I give you another conversion that you won't find in the tables, and that's 1 fluid ounce is equal to 29.5735 milliliters. Okay, so I want to figure out how much sugar in terms of mass is in this 8 fluid ounce serving of the kombucha. All right, so my given here is pretty much going to be the 8 fluid ounces. That's the serving size. Okay, I'm going to go ahead and give it another sig fig here, so it'll have a little bit of significance here. So I'll make it 8.0. All right, so let's say 8.0, and they'll follow that out with fluid ounce. Okay, now in our first conversion, I need to get from fluid ounces over to milliliters. And the reason for that is because I can then use the density to get back to a mass, okay? So let's do that first. 8 fluid ounces, okay? So I've got 1 fluid ounce in the bottom because I want to get rid of that unit. And now 1 fluid ounce has 29.5735 milliliters of kombucha in it. Okay, so fluid ounces will cancel with fluid ounces. Now, ultimately, I'm trying to get to a mass of sugar, right? So I need to get from a volume of the kombucha to a mass of the kombucha. Now, remember, the thing that gets me between volume and mass for a given substance is the density of that substance. Okay, and I have the density. We were able to, again, make that measurement using an independent method. So I want milliliters on the bottom because I want to get rid of that. So 1 mil of kombucha has a mass of 1.0231 grams. All right. So mils cancel with mils. I'm left with grams of kombucha here. Now, at this point, I'm well set up now to get back to the amount of sugar because I know the concentration of the sugar as a percent by mass. So now I have a conversion that gets me from grams of kombucha back to grams of sugar. And that's going to be that concentration. Okay, so what does that by mass mean? Well, it means that I've got 3.5 grams of sugar, which I'll just mention here, per 100 grams of kombucha. Okay? And I'll put KOM for kombucha here because everything prior to this has dealt with the kombucha. Now I'm moving from kombucha to sugar. Okay, so now grams of kombucha will cancel with grams of kombucha. I'm left with grams of sugar. Now, if I work this out, I'll say that's 8.47186 grams of sugar. Okay, and now I go back and look at my sig figs. Looks like I got 2 sig figs in the 8 fluid ounce. All right, it looks like the conversion I don't need to worry about. That doesn't limit me. The density is immeasurable, so it looks like I've got plenty of sig figs there. Looks like, again, in my percent by mass, I'm going to be limited to 2 sig figs. So it looks like I'm looking at 8.4, but I got to round up, right? Because I look to the right of the 4, I got a 7. So the 2 sig figs, I'm going to call that 8.5 grams of sugar in that 8 fluid ounce serving of kombucha. And again, that's a useful thing for somebody who's sugar sensitive to know. The other thing we can do from this is a lot of times people want to know how many dietary calories would be in the beverage. And it turns out there's a direct conversion between sugar in the form of sucrose, which is table sugar, and that's what we're measuring, and dietary calories. I think it's 4 dietary calories per gram of sugar or something like that. So we could actually go from there to dietary calories as well, and that's something else that could go on the food label. Okay, so here's a real nice real world example of how we might use a percent by mass as a conversion factor. Everybody okay with that? Any questions? Okay, good. Now there's one other sort of classic problem that I want to do that's kind of related to this. And that's example number 2 here. And this is a little bit more complicated. There's a lot going on in this problem. And the reason I like this problem, and I do it every year, is because you have to really keep track of identity of things, okay? So like in our previous problem that we did, we had 2 things we were relating. We had to keep in mind when we were talking about kombucha, but then at some point we're converting between kombucha and sugar. So identity becomes important. Okay, I had grams of kombucha, but I needed to get to grams of sugar. So I needed to keep track of those identities. Okay, so just keeping grams and mils and things like that isn't enough. At some point, we have to actually keep track of identities because we might have different grams of different things that we have to relate to each other. Okay, so here's a good example of that. So in normal blood, there are about 5.4 times 10 to the 9th red blood cells, which I'll call RBCs, per 1 milliliter. That looks kind of like a concentration, doesn't it? It's not a mass percent, but it's basically telling me how many red blood cells I've got per 1 milliliter of whole blood. That's concentration. It says the volume of a single red blood cell is about 9.00 times 10 to the minus 11 cubic centimeters, and its density is 1.096 grams per milliliter. Now, keep in mind here, we're talking specifically about red blood cells. Okay, so that's our identity here. So the question becomes, how many liters of blood are needed to collect 0.5 kilograms of red blood cells? So now we see what we have to do. We have a relationship we have to develop between blood and red blood cells that are in the blood. Okay, so what I want to kind of do is just write down some of these givens in here, or some of these things that are given in the problem, and make sure that I'm attaching an identity to them. Okay, so for example, I got a concentration. I can say, for example, and these are just conversion factors I'm going to use. I've got 5.4 times 10 to the 9th, is it? And that's RBCs, or red blood cells, per 1.00 mils of blood. Okay, so I'm going to make sure I write down blood there. So this is good. This shows me a way of being able to relate between red blood cells as a count and volume of blood. Okay, so that's going to be useful to us. Now I'm also being told that the volume of a red blood cell, RBC, is 9.00 times 10 to the minus 11th. Really tiny cubic centimeters, and that makes sense. It's a tiny little thing, but that's the volume of a single red blood cell. Now also I'm given a density. That density also refers to the red blood cell. Okay, so this is the density of a single red blood cell. All right, it's 1.096 grams per milliliter. So there are all my conversion factors that I can use with identities attached to them. Okay, so now I want to know how many liters of blood are needed to collect a 0.5 kilogram of red blood cells. So it looks like my given in this problem that I have to start with is going to be the mass of the red blood cells I want to get to. Okay, so let's go ahead and write that down. And again, I'm going to attach an identity here. So it's a red blood cell that I'm after. Kilograms of red blood cells. All right, so it looks like we can get between masses and volumes of red blood cells using the density. Okay, but I need to go from kilograms to grams in order to use the density. So we'll do that first. Okay, so I know that for every kilogram of red blood cell that I have, I'm going to have 1,000 grams of it. All right, so that's my first conversion. So kilograms of red blood cells go away. I've got grams of red blood cells. Now I'm going to use the density of the red blood cell to get me to a volume. Okay, so that's going to be my next conversion here. Again, we can just kind of string these things together so that we know in 1 milliliter of red blood cells, all right, I've got 1.096 grams. That's my density. That's per red blood cell, right? So we're talking about individual red blood cells here. Okay, so grams will cancel with grams. Okay, so that's my density. Now that takes me to milliliters, doesn't it? Now at this point, I can use my concentration, okay, to kind of get to a count of this thing, right? Because I know what the volume of a specific red blood cell is. Okay, so I know that one single red blood cell has a volume of what, 9.00 times 10 to the minus 11th. And that's in cubic centimeters, right? Which I could also write as a milliliter. Everybody remembers that a cubic centimeter is the same thing as a milliliter. Okay, so now what ends up happening? I can get volume of red blood cells to cancel. Mils cancel with mils. Okay, so now what am I left with? I'm left with essentially a count of red blood cells in the 0.5 kilogram. This is, if I stopped the problem right now, that would be what I would get. The number of red blood cells that are in 0.5 kilograms of red blood cells. But at this point, we're not done yet because we haven't accounted for concentration. So that's the next conversion that I've got to put in here. Now, the nice thing about concentration is that this is going to allow me to relate red blood cell count back to blood, right? So for every 1.00 mil of blood, that's where the red blood cells are coming from, all right? I've got a count of 5.4 times 10 to the 9th red blood cells. That's my concentration. So notice what happened here. It let me go from number of red blood cells to a volume of blood. And that's ultimately where I need to go because I want to know how many liters of blood I would need, right? So I got to get there. So I'm in milliliters of blood now, but I need to go to liters of blood, don't I? That's what the problem asks for. So I know that for every 1 liter of blood, I'm going to have 1,000 milliliters of red blood, or rather of blood, sorry. We're out of blood cells now. We're back in terms of blood. Okay, so blood milliliters cancel with blood milliliters. I'm left with liters. So now I'm in a position where I can go ahead and run through all the math here. So normally what I do is I just kind of multiply across and get a number, right? And then I take that number and divide individually by each of the things that shows up in the denominator. So when you end up with things like this, you kind of have to be a little bit careful about your math because there's a lot of stuff going on here. Make sure you catch everything. Okay, especially when you're dealing with these funny numbers in scientific notation, you know, like the 9 times 10 to the minus 11th and the 5.4 times 10 to the 9th. So a lot of times when I divide by those, I make sure I put those in parentheses in my calculator because otherwise it gets all confused with the exponents. All right, so when you do it, you might want to check and make sure you can get this value. I got 0.938692 liters of blood. Okay, now if you go back to your sig figs, again, we're multiplying and dividing. And it looks like the thing that's going to limit you here is going to be the kilograms of red blood cells. I'm looking for 0.5 kilograms with 1 sig fig there. Okay, so ultimately then I've only got significance to the 10th place here because of that. So now if I wanted to rewrite this, I would write this as 0.9 liters of blood that would be required to get me that 0.5 kilogram of red blood cells. Now, again, there's a lot of different things going on here, and this is a really, really good example of why identity matters. Okay, identity is huge here because in the first part of the problem, we're specifically talking about red blood cells, but at some point, we have to make the conversion between red blood cells and volume of blood. Okay, so that's why identity matters here. So if you go through and look at each one of these steps, make sure that you've not only got the correct unit attached to it, you've also got the correct identity attached to the conversion as well. Okay, so that's kind of a tough example, but I wanted to show you one of these ones that gets a little harder.
Excuse me, Professor.
Go ahead. Yeah, ask
Can
the
you
question.
please scroll up so I can get a screen cap of the problem?
Sure can.
And get the
That
problem.
good?
Yeah. Okay, I'm good. Thank you very much.
All right, no problem. And again, I'm going to archive all of this too. So if anybody ever misses anything, you can always go back to it. Any other questions about this, guys, or use of concentration as a conversion factor? And again,
Professor?
I show this. Yeah, go ahead.
Do you mind breaking down the math of it that got you 0.9?
Yeah, I mean, how would you like me to do that? Do you want me, there's a couple ways we could do it. Are you talking about actually how you get to a number or actually how we set the problem up?
How you got to the number?
How you get to the number. Okay,
Yep.
Here's how I would do it. Like if you're punching in your calculator with me, I would take my 0.5, and I like to go all the way across the numerator. So I would take my 0.5, multiply it by 1,000. Okay, then you have 1 times 1, so I don't do anything there, times 1 again, which I don't do anything with, times 1 again, which I don't do anything with. So you've got a value for the numerator now, right?
Yes.
Okay, very good. So now what I'm going to do is I'm going to start dividing. So I'm going to take that value you've got, and I'm going to start looking in the numerator for things that aren't ones. So divide by the 1.096, right? And you can go ahead and hit equal if you want to. That's fine. You can hit an equal after each one of these operations, and that'll sort of tell you where you are along the way. Now, the next thing is you're going to take that result, and you're going to now divide it by 9.00 times 10 to the minus 11th. Now, when you do this, you're probably going to want to put that in parentheses. Okay, so say divided by open parenthesis 9.00 times 10 to the minus 11th, however you put exponents into your specific calculator in parenthesis, and hit your equal again. And then once you've got that, you're going to do the very same thing with the next one. You're going to divide again by 5.4 times 10 to the 9th, also in parentheses. And then once you've got that, you're going to divide again by 1,000, and that'll take you there. And if you don't get my answer, my guess is that you're probably having issues with how you're raising things to a power in your calculator, because that sometimes happens as well. And again, how you do that sort of depends upon what kind of calculator you've got. But that's how I do it. I like to go through it step by step by step by step and make sure I've got it. Does anybody else verify my answer to be correct?
That's correct.
All right, thank you, sir. I did it a couple times just to make sure, because sometimes I will make a mistake. But sometimes it just takes a little practice with your calculator to kind of figure out how to get those numbers in. But it's a good skill to know, you know, and it's very much worth figuring out, because sometimes you'll run into these things where you've got really big or really small numbers you got to multiply by or divide by. So it takes a little bit of figuring out your calculator to do that. Okay, so at this point, what I want to do is spend some time over in Chem 101. We've got some more of these kinds of problems that we can work on, and I think I've got 20 minutes allotted for that, so that's exactly what we've got left. So let me pop out of here and hop back into Chem 101. I'm going to go back over to our in-class exercises. And we've got the dimensional analysis one. It probably won't take you 20 minutes to do, but we'll go ahead and start it. All right. And there they are. Oh, I put a blood problem in there too, but I don't think it's anywhere near as tough as the one we did here just a minute ago. Now, I'll give you guys a hint in the first one there. When it gives you the concentration of the gasoline in the crude, basically it's telling you what percentage of the crude can be converted to gasoline. You can kind of treat that as a volume percent if you want to. You could say, okay, you could say 45, you get 45 gallons of gas out of 100 gallons of crude. So that's perfectly fine to do there. It's just telling you a conversion factor between the two when you process the crude. So treat that as like a volume percent. That's the easiest way to do it. 45 gallons of crude for 45 gallons of gas for every 100 gallons of crude that you process. That's how I set it up, and it works fine. looks like we're making some progress there, guys. Yep, finally getting to that third problem. Good.
Professor, can I have help on the second one?
Sure thing. Like where would you like a starting point or?
Yeah, starting point. I'm assuming we have to make miles per hour or the feet into like miles per hour or the other way around.
Yeah, because your miles per hour is your velocity, and you're trying to actually get to a time that it takes, right? So basically, you're in a situation where you're going to have to convert your 60 feet, 60 inches. And you've got miles per hour, but you're going to eventually have to take that feet over into miles, right? Now, here's the trick with that. What's 60 feet, 6 inches expressed as a fraction? Like 60 point what? For example, 6 inches is what fraction of a foot?
Like
It's half a
half.
foot.
So it would be like
It's a half a foot.
60.5.
So you'd start with 60.5. That makes sense?
Yeah.
Yeah, and then you've got inches, right? So if you write that down, 60.5 inches. Now you got to get that to miles, don't you? So it jives with the velocity. And that's good because they give you a direct conversion between miles and feet. So you should be able to get to miles there. And then once you've done that, how are you gonna use the velocity? What goes in the top and what goes in the bottom?
Well, couldn't you just get the miles per hour, multiply that by 5,280 divided by 3,600? And that would
Well, I
equal,
don't. I'm just kind of working it out units wise in my head here. So I'm just
oh,
again using my dimensional analysis to get the units to cancel,
yeah.
right?
But-
So you've
Yeah,
got
but
miles now, right?
well, what I have is I have it as the miles per hour time like the 1 point the 105.1 multiplied by 5,280 divided by 3,600, and that gives me feet per second. And then I took 60.5, divided it by the number I got with that first equation. That's how I just got my answer.
Feet per second, and that should get feet to cancel. And then it looks like you're going to end up with seconds in the bottom of the bottom, wouldn't you?
Yeah, I got it right.
Okay. So that would flip to the top. So as long as your units work out, that's fine.
Could you still go through your dimension analysis, please?
Which one is that? Oh, with the dimensional analysis.
For the same problem, could
Yeah.
you still
Yeah, matter of fact, if you want to, I can break out to the other side there, and we can write it down. You want to? I can show it to you. So let me leave here and go back over into my notes. You guys are gonna have to kind of fill me in. So we said it was what, 60.5, and that was feet, right?
Yeah.
And I had to get
60.5
that in
feet.
terms of miles, did I?
Yeah.
So 1 mile is what, 5,280 feet? Okay, and then I had a velocity, didn't I? And that was in miles per hour, right? So in order to get the miles canceled, I have to have the miles part in the bottom, and I got to have the hours part in the top. So what was the velocity in miles per hour? I don't have it in front of me.
It was 105.1.
105.1 miles per 1 hour. Okay, so see what's happening there? I can get the miles to cancel with the miles, and that leaves me with hours. Now, did it want minutes, seconds? What did it want?
1 second.
Okay, so that's easy enough to do. You could do it in one fell swoop if you want. You could say that 1 hour is what, 3,600 seconds? Or if you preferred, you can break it down hours to minutes, minutes to seconds, which is where you get the 60 times 60, which is the 3,600s. So you can do it in 2 conversions if you prefer. That should give you the answer. Because notice what happens. Hours will cancel with hours and you're left with seconds. Does that make sense?
How did you know what to start with? I'm always confused by that.
How did I know what to start with? Yeah, I had to go to start with feet because actually, let me jump back there so we can look at the problem. Should just pop right up. Okay, so you've got a velocity there. Now notice that there are 2 units in that. I've got miles and hours, which tells me I'm going to use that as a conversion factor. I'm going to use that to get from miles to hours or hours back to miles, whichever way I got to go. Now it's asking me how many seconds. Okay, so that's telling me, all right, I'm looking for time. Oh, and conversion factor there, the 105.1 miles per hour has time in it, but it's a conversion factor that lets me get between distance and time. Okay. Now notice that the other piece of information in the problem is a distance. Okay. So, I've got a distance given to me. I want to get a time out of it. And I see a conversion factor there that will get me between distance and time. So that's how I know the 60 feet, 6 inches has to be my given. Because I can apply that conversion factor, which is the speed or the velocity, to get me to the other variable I want. Does that make sense?
Yeah, thanks.
No problem. Yeah, it takes a little practice, but yeah, you'll figure it out. Just takes doing them. Good questions, guys. See how we're doing on that last problem. 18 folks. See, it's a good thing we did that blood problem, huh? You guys are nailing that last one. We got about 3 minutes left, folks. Anything else you want to ask about any of these problems? Yeah, it looks like you guys are doing fine on these. All right, so just the last minute or two of class, I just want to remind you guys of just a few things. Friday is upon us, right? So remember, you get a different kind of quiz on Friday. We're going to do a Friday quiz. So remember, a Friday quiz is a bigger quiz, and it covers everything we've done in the week, okay? So basically, anything we've covered in the course up to this point is going to be fair game on the Friday quiz. So you want to make sure you're kind of keeping on top of those homework problems. Pretty much anything in chapter 1 at this point is fair game because we're moving into chapter 2 with the next video, okay? So I noticed a lot of folks have been working ahead and doing really well on the chapter 1 homework problems. Keep going at it, guys. You know, get as many done as you feel comfortable doing. Try to make sure you're working representative problems of all types because those are the kinds of things you're probably going to see on the quiz. Okay. By the way, homework number 2 for chapter 2 is open. I've already noticed some folks are already working ahead on it, which is fine. But that's where the video is going to go for Friday. So we're going to introduce the atom. All right. So that's kind of where we're at. So make sure you're ready on that Friday quiz, guys. Yeah, go ahead.
Is today included in Friday?
Yep, today would be included in the Friday quiz. Correct.
Okay. Okay.
Is that going to be during
Definitely.
class like the other ones?
Yep. It's just you're going to end up getting a little more time to do it. That's all. So it'll be a little bigger quiz. It'll probably have maybe a couple more questions and you'll get more time to do it. Same formula applies. So practice, practice, practice is basically what it comes down to. And make sure you catch that video because I could certainly ask you something from the atoms video that you're going to have. All right, everybody good? All right, I think I'm there. So I'm going to go ahead and sign out. And again, thank you guys for coming around. Thanks for the good questions. And I'll see you guys on Friday.
The video you were talking about was your YouTube videos, right?